Good morning, everybody, from my side, from Germany, or good afternoon, good evening, depending on from which time zone you are joining us. Welcome to Park's webinar series, Exploring the Horizons of 2D Materials. My name is Justyna Sliwa, and I'll be moderating today's session titled Dynamically Rotatable van der Waals Heterostructures. So our 2D materials expert today is Rebecca Ribeiro-Palor from the Center of Nanoscience and Nanotechnology in France. And let me give you a few information to webinar's content and the procedure today. So in her talk, Rebecca will explore a dynamic device architecture that enables the twisting of 2D material heterostructures, and she will reveal how adjusting the interlayer rotation angles in graphene encapsulated by boron nitride affects electronic properties, more superlattice effects, and the activation of a ferroelectric state. And a few words about Rebecca's career path and research focus. So Rebecca's impressive research career spans 3 continents, South America, where she received her master's degree from the Venezuelan Institute for Scientific Research. After moving to France, she obtained her PhD in physics from the University Paul Sabatier in Toulouse and did her first postdoc at the French National Metrology Lab. After moving to US, she worked as a research fellow at Columbia University, dealing with in situ band structure manipulation of van der Waals heterostructures. And currently, Rebecca works as CNRS researcher at the FUNANO group, and her research focuses on investigation of the generation and control of different topological orders in van der Waals heterostructures. Notes, yes. That's all from my side. So I'm very happy to welcome now Rebecca. And Rebecca, the stage is yours.
So thank you very much for the invitation. I'm very happy to be here. I really appreciate that you organize all these webinars and the different topics that you are presenting, which helps a lot. At least my students have been learning a lot about AFM in your webinars. So today we are going to talk about dynamically rotatable van der Waals heterostructures. So this seems like a very complicated title, or at least a very difficult to understand. But it's in fact just the consequences that have rotating 2-dimensional materials on top of each other, and how by using an AFM we can in fact control in situ this angular alignment. So for the whole talk, I'm going to focus only on van der Waals heterostructures made of boron nitride and graphene. Although you need to know that these can be in fact used by for any combination of 2-dimensional materials. So what you are seeing here in the first slide is one of my favorite AFM images. This is a piece of bilayer graphene deposit on top of boron nitride. And you can see these hexagonal patterns that forms on top of it. And in fact, this is a moiré superlattice. We're going to see what's a moiré superlattice. But just so you know, this is the consequence of the alignment between the 2 layers. So let's just start with the basis, okay? So we cannot talk about van der Waals heterostructure without mentioning first graphene. Graphene, it's a 1-atom thin layer of carbon arranged in an hexagonal way. You have 2 atoms per unit cell, what we are going to call A and B, but for the rest of the talk, they are going to be undistinguishable. They are both made of carbon, so we cannot really tell them apart. So the way most of the researchers or graphene is made in most of the academic laboratories is by exfoliation, by mechanical exfoliation. It's what is the so-called Scotch tape method. You hear probably about it because Kostya Novoselov and Andre Game got the Nobel Prize, not just for developing this technique, but this technique was what allowed them to prove that graphene was really a two-dimensional material. And where do you find the building blocks of this sketch tape technique, which is in fact just graphite? Well, the most common source of this is a natural graphite. You can find it in mines, but you can also have it as a byproduct of certain industrial processes. So, okay, we have a big piece of graphite. We take Scotch tape, we put the graphite on top of this Scotch tape, and we peel on enough until we obtain, as you can see in the picture, so my pointer is really bad. Ah, there it is. There it is. Until you obtain kind of a continuous, it's not continuous, but a kind of a thin layer of graphite on your Scotch tape, and then you deposit it on a substrate. However, not every substrate can be used for this. You need a very specific substrate to be able to observe graphene, which is silicon oxide of a very precise thickness. So there are two thicknesses that are most used, 90 nanometer silicon oxide and 300 nanometer silicon oxide. So you were wondering, why do we need this? Well, because you can see in this picture, as you can see in this picture, graphene, not like, okay, there it is. Graphene, it's very transparent. In fact, it only absorbs 2% of the light, and then it becomes very difficult to find it optically. But also this makes it very attractive to make transparent electronics. And talking about electronics, electronical properties of graphene, as you might have heard already, are very good in terms of the electron mobility. It's very high because the energy dispersion of graphene, it's linear, differently to other semimetals or semiconductors. Graphene is not a semiconductor, it's a zero gap semiconductor. Let's clarify that from now. So it has a very high mobility of electrons, which ensures a high conductance and makes it also very attractive for electronics. So let's use or explain the building blocks of all the experiments we do. We take graphene, that I already explained you what it is. We know what are the electronic properties, and what we are going to do is we take the same flake or a flake similar to the one that I had already shown you. We go to a wonderful clean room at C2N, and we make electronic devices, which means that we connect electrically this layer through electron beam lithography, metal deposition, and reactive ion etching. So once we have this electrodes contacting our device, we're going to measure electron transport or charge transport, to be more precise. So it's quite simple. The measurements we perform, we apply a current, we measure a voltage. Seems very simple when I say it like that. It's a little bit more complicated, but we will get into it later. For the specific case of graphene, we have a property that is very important, is that we can apply through a capacitive effect, we can change the Fermi energy or the number of carriers in our material. So let's say that, for example, we want to measure the resistance of this graphene flake as a function of this gate voltage. So what we'll find is that as we change the gate voltage, we have a strong increase of the resistance once the Fermi energy crosses the point where the conduction band and the valence band touch each other. And you're going to see it again. You can see in the right side that the Fermi energy crosses the charge neutrality point, and that's where the resistance of graphene strongly increases. So, and in fact, this is one of the most important characteristics, electronically speaking, of graphene, is the existence of this charge neutrality point, which in fact allow us to change the nature of the carrier. So we can have carriers made of electrons or made of holes. We have a hole or an electron conduction. So now you can imagine that we have graphene, but we have many other two-dimensional materials. And in fact, in 2013, which is more than 10 years ago, the family of two-dimensional materials was already quite large. And it has kept increasing during this time. The list of two-dimensional materials today, it's enormous, and I don't like to show it because you will see almost nothing. But for the rest of the talk, as I told you before, we are going to focalize only in graphene and boron nitride. So boron nitride is, structurally speaking, the equivalent of graphene because it's also an hexagonal lattice, but this time, instead of carbon, we're going to have boron and nitrogen atoms. And the fact that we change carbon for boron and nitrogen atoms also give you a slightly larger lattice structure. In fact, it's 1.8% larger than graphene. So now we have all these materials, and what can we do with them? Okay, so of course we can study each one of them independently, but also, and maybe more interesting to me, is that we can put them together and make van der Waals heterostructures. So the way van der Waals heterostructures are built in laboratories now is mostly, there are new techniques, but it's mostly through the dry layer assembly technique, which consists on taking polymer, in this case is PPC, polycarbonate, and using this polymer to pick up a first layer of 2D material. In this case, it will be boron nitride, and then we're going to pick up with this one a second layer of another 2D materials. In this case, it's graphene. We're going to do this so on and so forth until we get a final heterostructure where our active layer, for example, boron nitride, graphene in this case, is encapsulated between two layers of boron nitride. So now, this is a false colored optical image of a stack, that's how we call them, of a stack of boron nitride, graphene, boron nitride. And if we make a cross-section of this material, and we observe it by TEM, we can see that there is nothing between the layers. So there is nothing gluing the layers together. Here we are really talking about materials that are held in each other by van der Waals forces. That's, of course, why they are called van der Waals heterostructures. So, okay, we can put these materials on top of each other. We have boron nitride, which is an insulator. So, in principle, doesn't conduct any electricity. It should not modify the structure or the electronic properties of graphene. However, and that's what we thought, at least in 2013. However, we're going to see in the rest of the talk that this is not that simple. And in fact, every time we put one layer on top of each other, they are going to see each other in a certain way. They're going to interact with each other. So putting layers on top of each other not just give you the possibility of encapsulated materials, but also of mixing different materials to share their properties. Like, for example, inducing a spin-orbit coupling in graphene when you put it in proximity with a material with a strong spin-orbit coupling. You can also change the conduction of graphene, change the doping of graphene. And these new degrees of freedom that were not available before with, for example, more conventional structures such as gallium arsenide, aluminum gallium arsenide, are very new and, let's say, completely related to van der Waals heterostructures. So now we have different materials. We can put these materials on top of each other, but more importantly, now we can design, in fact, the properties of our materials. And one of the methods that is preferred method in my laboratory is through the control of the crystallographic orientation of the layers, because the fact of having independent layers, independent materials that can be stacked on top of each other, not just allows you to stack them, but to change this crystallographic orientation. And you might think that, okay, but this my modified electronic structure if I'm talking about two active materials, like, for example, two layers of graphene. And in fact, that's the case. That's, let's say, the most famous result of twisted materials, which is the first observation of superconductivity in graphene in two layers of graphene that are on top of each other with a very small angle. In fact, this result is not just very important by itself, but it also reflects how much this angle relation changes the properties of the material. And here you can see we have two curves, one that is taken, for example, with 1.16 degrees, which you can see a critical temperature well below 1 Kelvin, and another one that it's 1.05 degrees with a temperature that is below 1 Kelvin. So you can see a small change in the angle, in the angular alignment, can give you a strong modification of the properties. So, okay, here it's the example of two active layers of graphene. However, what I'm gonna talk about is just one layer of graphene and a layer of boron nitride. And in principle, boron nitride is an isolator, so it should not modify the electronic band structure of graphene. Okay, but in fact, since the two lattice structures of graphene and boron nitride are so close to each other, then you have, when they are crystallographically aligned, you have an effect that is called a moiré effect that you can see here. This is just an optical illusion. It's a representation of this moiré. But I'm going to explain you just in a second a little bit more in detail how it is and why it is created, this moiré. So this moiré, in fact, will strongly depend on the angular alignment, as you saw in the previous animation. And you will have the length of this moiré that will strongly decrease with the angular alignment, and then it will strongly increase as you realign. So it will be periodic. Every 60 degrees, you will have this moiré. So the moiré structure, in fact, comes from the fact that not every carbon atom is going to have the same environment now. So, for example, here you can see, if you focalize in this part where you can see only red dots, you can see that the graphene, the hexagons of graphene in this area will not have the same environment as another one nearby, okay? But at a certain distance, called lambda, that is the size of this moiré superlattice, you will recover, again, the same environment, okay? So this is the origin of the moiré structure. So this different environment in each carbon atom, so will give you a different charge distribution, so different properties locally. So this is very beautiful, and it's an easy way to understand the moiré superlattice. However, it's not the whole story. If you look with STM, in this case, so if you do STM spectroscopy, or scanning tunnel microscopy, sorry, what you can observe is that depending on the crystallographic orientation, you will recover moiré of different sizes, as I told you before. But after certain alignment, you recover a structure that is a little bit different. You can already see, for example, that the structure at 6 nanometers and 2 nanometers moiré is not exactly the same as the one at 11 nanometers moiré. And what is happening here is that the moiré inside the moiré cell, that is this one here, you will have a strain. In fact, the carbon atoms that are sitting on boron nitride, they will enlarge to match the lattice of boron nitride that I told you before is 1.8% larger than graphene. And they will propagate this strain will propagate until it cannot hold it anymore. And then it will release it in the form of wrinkles or corrugations, for example, that you can see around here. This is what we call the commensurate state. And in fact, you might intuitively think, okay, but then it's not just the moiré, then this stretching will also modify the electronic properties. And this is basically what we are gonna discuss today. So let's just one slide more and I go for questions because I saw that I have a comment. So let's go back to our previous example of we are measuring transport. So we are measuring the resistance as a function of the gate voltage or the position of the Fermi energy. As I told you before, the example I gave you at the beginning was we have graphene on top of boron nitride, for example, and we are completely misaligned, so 30 degrees. And we have the same linear energy dispersion as we saw before. Now, as I told you already, we will have a strong increase of the resistance close to the charge neutrality point. If we add to this, if we realign the system, we will modify the electronic band structure. We will have these replicas of the charge neutrality point at lower energies. And now the transport properties will be different. For example, we are going to see when the Fermi energy crosses these satellite points, we are going to have a strong increase of the resistance. This is what is called a satellite peak. So I'm going to stop here for a second to see the question. Justina, can you?
Yes, Rebecca. So we have one
Yes.
question from, I don't know how to pronounce your name, H. I just gave you the permission to talk if you want to ask your question yourself. Otherwise, I can read it loud.
If anyone has a question, I will be also happy to answer.
Yeah. Okay, he's not, he or she is not unmuting himself. Okay, so let me take it. I will read it loud. The STM images, are the STM images measured in ambient or in high vac, so in vacuum condition?
Vacuum condition. In fact, it's low temperature STM. It's 4 Kelvin STM. But you can see them at even room temperature, the commensurate state. It's you can even see it with AFM. In fact, I'm going to show that in a second.
All right, thank you. Oh, there is a second question from Sai Mohan. I'm sorry if I'm pronouncing your names in a not correct way. Let me just unmute you. All right. Would you like to ask your question yourself? There we go.
Yes, hello.
Hello.
Can you hear me?
Yes, we can hear you.
Yeah, so my question was, can we see these moiré superlattice patterns in the morphology as well?
Yes, I mean, I guess with morphology, you mean the topography
Yes.
of the AFM. Yes, in fact, the first image that I show at the beginning, it's an AFM image, and in the next slides, I'm going to show you the more examples of this moiré. But yes, we can see it. We can see it in lateral force microscopy, for example, or even in tapping mode. If it's big enough, you can see it.
Thank you.
Okay, so we were talking about moirés, and now we know what's the transport response, the electron transport response for a fully aligned, that is 0 degrees alignment, and for a 30 degrees alignment graphene. Okay, so this is very beautiful. We have a modification of the electronic band structure. Please remark that these measurements are made 300 K, which is room temperature. Now, what we decided to do at the time is we wanted to go from one to the other, from one alignment to the other alignment in steps. Because what you don't know, what I didn't say before, is that the way to do this is you stack the materials and they are fixed. You cannot change the angle anymore once you measure the transport. So in 2018, we developed a technique that using an atomic force microscope tip allow us to change the direction between the crystallographic alignment between these layers. So the way we do this is we predefine our device. Here, what you have, it's boron nitride on the bottom. Then you have a whole bar made of graphene, that is the dark side here. And on top of it, we're going to deposit a layer of boron nitride, but this layer of boron nitride is in fact pre-shaped in a way that we can rotate it. And you can see here, for example, the motion of these, we call them handles. These handles, okay, we rotate it continuously. Now, the other step, extra step that we did for this was we installed electron transport measurement inside of our AFM, which in fact allow us to measure every single angular alignment for these cases between 0 and 1.6 degrees. So we can now measure transport and we can stop at any angle that we want. And okay, this is beautiful, but what else can we do with it, no? So since our devices are built in a way that they do not depend on the AFM is used to change the angle, but they don't need to be inside the AFM. We can also measure optical properties. Here it is, for example, Raman spectroscopy of alignments of different crystallographic alignments from 0 degrees to 2 degrees, where you can see that the 2D peak of this Raman spectrum gets larger and it decreases. This is because you have phonon band, and this phonon band is getting folded by the presence of the moiré superlattice, the same way as the electronic bands get folded by the electronic properties. So, okay, we have transport and we have optics, but we are inside an AFM. So we can also measure mechanical properties. That's another thing we did at the time. We use these handles and the friction detection of the AFM, that is just the lateral bending of the tip, okay, to measure the friction response. And you can see that every time we are aligned, we cross the alignment, so every 60 degrees, we observe a strong increase on the friction, which is reflected by the presence of this moiré superlattice, which increases the friction because van der Waals forces will be stronger at that position, at the line position. So what else can we do? Well, other groups since then have also used this technique for different methods, for example, to make double aligned devices, which means that they align at the top and the bottom layer, and they can see the effects of symmetry breaking and symmetry restitution, which are also observed in second harmonic generation. So these are optical measurements. Here we have different handles at different orientations. So we are gonna either restore the inversion symmetry of the system, and that's where we don't see any response. Like here, for example, there is no second harmonic generation, or we are gonna break completely the second harmonic, this inversion symmetry on the interface, and that's where you have a strong second harmonic signal. And more recently, also at Columbia University, they develop a technique that use these beautiful handles pushed with AFM to make vented systems. So these vented systems allow us to control the angle locally, which means that we're going to have a gradient of angular alignment through the whole ribbon, and also to create the strain. So now you can control the optical properties, mechanical properties. You can create at will strain. So it's a kind of a powerful technique. So for the rest of the talk, what I'm gonna tell you about is the electronic properties that we found mostly at room temperature for bilayer graphene. So the setup is basically the same. we have a whole bar made of bilayer graphene. We have a gate, a graphite gate, so electrostatic gate. There is a layer of boron nitride between these two that I'm not showing for just to make the figure easier to understand. And we're gonna have this BN handle again. So before we were talking about monolayer graphene, and now we're going to talk about bilayer graphene. We're going to see the difference between these two. The technique is the same. We still use the AFM to push this handle around and therefore change the crystallographic orientation. So if you remember before, we were at the room temperature and we could see this very prominent peak that we call satellite peak moving with the crystallographic alignment, moving in gate voltage. Now the case for bilayer graphene is slightly more complicated. In this one, we do not see the presence of any satellite peak at room temperature. There is nothing. This is very well understood. It's the fact that you have a broader peak. A broader peak that will merge, in fact, with charge neutrality at room temperature. But you can still see that there is an increase in the charge neutrality point and an enlargement of this peak. In fact, if you follow this increase, you're going to see that it's periodic. Every 60 degrees, you see an increase. But you already, if you see this curve carefully, you already know that, well, it doesn't seem to be the same every 60 degrees. It seems to be 120 degrees. So to confirm this, first, we took the largest layer, the largest peak, and we went to low temperatures to see if we really are aligned at this position. We could observe the presence of the satellite peaks, the same satellite peaks that we were talking about before. So good news, we are aligned. That's already something. Now, if we do the same for several of them, we can see the peak moving, okay, which reflects that we are really changing the alignment. I mean that in these strong peaks, we are really getting close to alignment, okay? So, okay, we are getting to alignment. What are we going to do? Why is 0 and 60 different? No? So we're going to focalize, in fact, in those alignments. We're going to see what happens at 0, what happens at 30, 60, and 120 degrees, because they do not seem to be the same. Okay? So if we go to low temperatures and we see them, they have a small difference. At room temperature, they also have about the same difference, but nothing major. However, if we remember before, when I was telling you that there is this commensurate state where you have all the strain distributed, we think that this commensurate state might be at the origin of this difference. So we ask our collaborators in Louvain-la-Neuve to make numerical simulations of what's happening to each one of these layers. How is this commensurate state? So if we look at the first layer, that is the one that is closest to the boron nitride, we don't see almost any difference. Now, if we go to a second layer, okay, we can see that there are a few differences between them. The origin of this difference is that if we look at what's happening at 0 and 60 degrees in the commensurate state, so where graphene already stretched to match the layer of boron nitride, we can see that, in fact, the second layer, the one that is far, in one case, we'll see only boron atoms, and in the other case, we only see nitrogen atoms. And we are just talking about van der Waals forces. So nitrogen and boron will not have the same effects on carbon, even if it's a second layer. And that's why that is the displacement of the atoms in the plane, will be stronger in one of the cases and weaker in the other case. So first, why do we know that we have this commensurate state? As you asked before, how are we sure that this it's really in a commensurate state. So we did AFM measurements of an open phase graphene, and we can see very well, I would say, the moiré state. And as I told you before, the first picture that I show is in fact boron nitride on the bottom, graphene, bilayer graphene on the top, tri-layer graphene in this spot, and 5 layers in this other spot. So this moiré superlattice is not just concerning the first layer, it's even propagating to a much larger number of layers. So, okay, we know 0 degrees and 60 degrees, they seem to be different. This is most likely related to the atomic configuration of this. So we wanted to go one step further with this technique, and we developed a new sample architecture that in fact allow us to change the crystallographic angle, measure the transport properties in situ, and have an electric field that is perpendicular to the system. So not just the regular gating effect that we were using before, but now we are able to apply 2 different gates to the system in order to keep the carrier concentration constant, but change what we call the displacement field. The displacement field will make the wave function of graphene localized either in the bottom or in the top layer, depending on the sign of this displacement field. Here's a beautiful AFM image of these kind of devices that were made possible thanks to the application of graphite flexible electrode on top that connects electrically a macroscopic contact to our top gate in the handle, which is made of titanium and gold. So how do we know if these top gates work? Well, bilayer graphene has this property that when you apply a displacement field, you can open an energy gap on it. What happens when you open this energy gap at the charge neutrality point is that your resistance will strongly increase. So here we have the example of one of these devices where we are changing the back gate for different values of the top gate. And you can see that we have a strong increase of the resistance, and then a strong decrease and a strong increase. So which means is here in the middle, we have a fully closed energy gap. And as we go in one sense or in the other, we have the opening of this energy gap. I think there is one question. Justina, can you?
Yes.
Yes.
Yes, it's again Saimohan. Would you
Yeah.
like to unmute yourself and ask yourself?
Yes, hello. So these rotations, I was asking the question, how do you do that? Like it is a programmed manner, or is it like individually, manually, you're rotating this?
So manually, I don't know how it will be. Of course, it's the software of the AFM that allows you to describe a vector, and you just tell to the AFM, and you use the software of the AFM to tell it from point A to point B. You're gonna change from, for example, the tapping mode that we were using to see the device to contact mode. So, and disconnect the feedback. So what it does is you have the handle and your AFM tip will come to point A, will move to point B in contact mode. As the feedback is desactivated, you will not go above the device, but you will push it. And since they are free to move, they are not, they don't have contacts, rigid contacts or anything. They are just gonna be displaced. They are just gonna move from one side to the other. Was that clear?
Yeah, it is clear. But how much of the movement is rotation? Then I mean to the translation movement.
So yes, of course, they do not just translate. You can have several schemes to make them rotate more than translate, but there is always a small translation. So the translation for us is not a big problem, because the first thing we do when we are working with a new system is we fix the handle in an angle that we know that is very sensitive, so most likely fully aligned, and we start translating it, and see if there is any effect. So far, we haven't seen any effect of translation. The only effects that we see are rotation, but there is always a translation component, yes.
Yeah, thank you.
Well, is there any other question that I may answer right now?
I do not see anything in the Q&A panel.
Okay, so I
guess, yeah, move on.
Yeah.
We can always
Okay.
have a final discussion at the end of your
Good.
presentation.
Good, thank you very much, Christina. So, okay, we can change the gate in both senses, and we can also change the alignment. So now we can do a little bit the same that we did before. So we compare 0 degrees, 50 degrees, and 60 degrees of alignment. And they, to be honest, they don't seem very different, much more than what we saw before. Some peaks are higher, some peaks are lower. However, if you look at it more carefully, you will see that the position here, the signals in white, okay? The black dash line are the center, is the 0, 0 position. So in white, you can see the position of the minimum of the curve I showed you before. So we are gonna follow this curve, okay, which is the same, it's a different, the color plot that I show you after is just a different representation of this kind of plots. So we're gonna follow the minimum. Why the minimum? Because the minimum is the position where the gap is fully closed, okay? And at this position is in fact where graphene it's really in its natural state, which means that there is no remnant electrical field created by the van der Waals forces. Okay, so you can see that for these three, it's already different. Okay, you don't have the same position for the three of them. Here you have the value of this intrinsic displacement field, and you can see it varies a lot from one alignment to the other. So I'm just gonna skip this for a second because it's gonna be confusing if I say it here. And I'm just gonna remind you what I'm doing. This time I'm gonna follow that minimum, but at room temperature, okay? So what I'm gonna do inside my AFM is I'm gonna fix an angle, and I'm gonna measure my resistance as a function of the gate going in one direction and in the other direction, okay? So these are different values of the top gate that start here and goes up to here, and then it goes from here to here. If I follow these points, the maximum of the charge neutrality point, I'm gonna see two parabolas, one that is moving in one direction and the other one moving in the other direction. And there is a minimum for both of them. And that minimum is, as I told you before, where the energy gap fully closes, okay? If I take that point where the energy gap fully closes for the values of the top gate and the bottom gate, and I extract the displacement field that I told you before, is the electric field penetrating the material when my charge carrier density is 0. So if I do that, what I'm gonna obtain is this beautiful curve. So I know it's not that intuitive at the first time, because what you have to think here is this displacement field, this displacement field that I'm extracting is in fact how much electric field should I apply to have the closing of the energy gap, which means how much electric field do I have to apply to compensate the natural electric field created by the presence of the boron nitride, okay? So this is in fact well known for in solid state physics. This is called the crystal field. So the field, the electric field created by the presence of the atoms in a unit cell, okay? So if we can see this curve in a little bit more detail, we're gonna see that, of course, it's changing. We will expect it to change as the atoms are farther from each other and then closer to each other. So we expect it, since these are hexagons, we expect this to have a 60 degrees symmetry. We know that graphene has a 60-degree symmetry, but boron nitride has a 120-degree symmetry. So it means that here, since the periodicity that we see is 120 degrees, means that we are inherent the symmetry of boron nitride. And the last very important point of this curve is this very pronounced dip close to fully alignment that we can see here, and that in fact we can slightly see here. Okay, I'm gonna go back in a second to the origin of those dips, but before that I'm gonna tell you that there is something else that is changing in my sample when I do this this rotation of the handle. So the electric field, the intrinsic electric field of the system created by the alignment of the layers is changing, okay? But also the carrier density, the doping of my sample will change. And they are, of course, changing in the same way because they are strongly related. This intrinsic carrier density is strongly related to the displacement field, okay? And the reason why these two are changing, as you might expect so far, is because of the carbon and bottom atoms and how they arrange with respect to the bilayer graphene. So for example, here we have the lattice structure of bilayer graphenes. This is layer 1, this is layer 2, layer 1 is on top, layer 2 is on the bottom. In bilayer graphene, what really matters to have a displacement field is the difference in electric field felt between, or that you can find between A1 and B2 atoms, okay? So you can see that for a 0 degrees alignment and a 60 degrees alignment, you will not have the same difference, okay? You will have a different state or a different charge concentration and charge difference between these two layers, which give rise to this difference between 0 and 60 degrees. Now, if you look at this, at the big dips that I told you about and the small dips at 60 degrees, you might wonder, okay, but if it's not coming, if it's coming from how the atoms arrange, what happens with graphene in the end, that they don't have the same lattice, but there is the commensurate state. So we asked our colleagues in Louvain-la-Neuve to make numerical simulations for us and calculate this intrinsic field. So how this intrinsic field should be, just thinking on atoms on top of each other, how they behave. Okay, so we can see in this curve that what we'll expect intuitively, because it's also a very intuitive result, is that when we are aligned, atoms are closer to each other, so they will feel a stronger electric field, which is the case here. So you can see it increases every 60 degrees, but this is periodic and it does not look like our previous curve. But you will also realize that this is an unrelaxed system. This means that this is just rigid graphene on top of rigid boron nitride. So now if you relax the system, you can see that this curve now resembles a lot more to our experimental curve. And in fact, what we are seeing around here, that I have been promising you to explain to you for for a while now, I'm gonna use better the experimental results. It's in fact the commensurate state. So this is the response, the electrical response to that change, that stretching inside the moiré cell that I explained you at the beginning. So this is how the system is responding electrically, or how the band structure is responding, how the localization of your wave function is also responding to that intrinsic stretching of graphene with respect to boron nitride. So this curve is explained. This is very beautiful, but there was something in this curve that I didn't tell you about, which I also find very beautiful. So you can see, if you're an experimentalist, most probably you already saw it and it's bothering you as much as it bothers me in this curve, is this part of the curve where you see a lot of points that do not seem to behave as well as the rest of the points. They seem a little bit noisy. So it's not a problem with our sample. It's in fact, when you are stepping there and you make a gate-gate map, you observe this. And this is an hysterical behavior close to charge neutrality. In fact, this is the position of charge neutrality. The red dots are when the gate is swept to the right, and the blue dots are when the gate is swept to the left. So you can see that at the beginning, the points are on top of each other, pretty much on top of each other, and then at some point they start to have an hysterical behavior. So if we take the sample in that alignment, that specific alignment, and we go to low temperatures, we can observe that, in fact, yes, it's an hysterical loop. It's a very well-defined hysterical loop that has been recently associated with ferroelectricity, with a ferroelectric behavior. So what it means that our system is being polarized, the position of the layers, the control of the alignment between the layers, take them to a metastable position where you have dipoles, and these dipoles are getting reversed, getting switched by the gate. So if you go in one direction, you get your dipole in one alignment. If you go in the opposite direction, you get them to switch in the opposite alignment. So this also happens if you use, because, sorry, I didn't give you the details, but here we're using the top gate as a fast axis and the bottom gate as a slow axis. If we change the axis, the slow and fast axis, you can see that we do not recover that behavior anymore. However, if we go down with the same gate, we recover the hysteresis, because this one and this one do not follow the same path. So for the moment, we have a strong hysterical ferroelectric behavior started by the crystallographic alignment that we control with our AFM. We also found something quite interesting, and I just, for full disclosure, this ferroelectric effect has been already reported by 3 groups in the world. It's has been mostly reported in fixed angle devices. They do not know how to reproduce it, and they always associate this with the formation of the moiré superlattice. However, you can see here that we are not in the aligned position. We are close to a misaligned position, so we should not have any moiré superlattice, and we don't see any moiré satellite peaks. So it means that we are not necessarily aligned. However, we also observe this behavior for an aligned position, for an aligned device, a different device. You can see the satellite peaks. We can observe this erratic behavior of the gate, which is associated with the ferroelectricity. In this case, both gates are symmetrical, which is different than before. But more importantly, when we are aligned and we observe this ferroelectric state, it's a very unstable state. In fact, these are just different cool downs of the same sample. You can see cool down 1, we saw a beautiful ferroelectric state or hysteretical state. Then for cool down 2, it's almost gone, and for cool down 3, it's practically gone. So with this, since I'm running out of time, I would like to give you the take-home message of this talk is bilayer graphene aligned with boron nitride has 2 different moiré superlattices. The observation of these different electronic properties of moirés in the same material, it's only possible because we can change the alignment of the layers in situ, and because we have this dynamical control of the layers, and we can observe this ferroelectric behavior that we are looking forward to observing it in AFM images very soon as well, which is not, in fact, differently to the proposal of the MIT group, this is not related to the moiré superlattice. And with that, I would like just to thank you for your attention and the people that really did the job in the lab.
Great, thanks so much, Rebecca. So it's time now for the final Q&A. So the question to all attendees, are there any other open questions which you would like to ask Rebecca? Now it's the time to do that.
I just unmuted myself. Hi, I'm Andrea. I would like to ask a few questions about boron nitride, actually. So how thick are the top and the bottom layers?
Okay, in most of our devices, the bottom layer is always close to 60 nanometers, just because it makes it easier for us to make the device. Okay, you have kind of a sweet spot when you make the van der Waals heterostructures. The top BN, it varies. We have tried from 20 nanometers to around 100 nanometers so far. So.
Okay, and the beautiful lateral force microscopy images that you showed are were these acquired with a top boron nitride layer or without? So can you see through?
No, so those were acquired with open phase devices, which means that you have boron nitride and graphene on top, and then you just scan the graphene.
So directly on graphene, yeah.
Yes.
And most
so
of
just a precision. The Manchester group has measurements of graphene aligned to boron nitride, where they put up to 10 layers of boron nitride on top, and then they can still see the moiré, but we don't know what's the upper limit.
Okay, but moiré in lateral force microscopy or okay?
Yes, in lateral force microscopy.
That is also interesting. And so the last question is, you are showing results from electrical results from transported through the whole device. I was wondering if there is any information that you could get, for example, through the AFM probe using some electrical mode. If there is some information that you could get at high resolution via doing AFM on the top of your graphene.
Yeah, in fact, we are developing new samples right now that are kind of the equivalent of the top gate samples, like the equivalent of these ones, but with very thin boron nitride and with platinum instead of gold to measure the ferroelectric response, to see if it's a real ferroelectric response. So yeah, we are gonna use our wonderful AFM for that.
Okay, thank you very much.
All right. Thank you. Thank you from my side too, Andrea, for your questions. Let me wrap up the webinar. So thank you so much, Rebecca, for your great presentation, and thank you to all attendees. All right. And with that, thank you once again. Thank you, Rebecca. Thank you, all attendees. Thank you, my colleagues, for your help, and have a nice rest of the day.